All right, our next speaker, the second spotlight of this session is from Piotr Mirowski, and he's going to talk about learning to navigate in complex environments.
Hello, I'm very happy to talk to you today. This is learning to navigate in complex environments, done with many great people at DeepMind, in particular Razan Pascanu, who originated the idea of depth prediction as an auxiliary task for reinforcement learning, and Raya Hatso, who has been leading the project. So this project was done in 3D environments, which are now available through DeepMind Lab, and you can download them on GitHub. And we focused on a specific subset of those environments, which are navigation mazes, where there typically is one goal represented by a floating red shape, and additional sparse rewards yielding 1 point. The goal yields 10 points. Those sparse rewards are fruits. During the episode of one game, the agent spawns randomly somewhere in the maze, then tries to find the goal, and once it finds the goal, it gets teleported randomly somewhere else in the maze, and then tries again to find the goal until time elapses. And there is a fixed duration of time for each game. We considered multiple combinations of environments. For instance, we looked at the simple I maze, where there are literally only 4 branches, and at the beginning of each episode, the goal is randomly assigned to one of the arms of the maze. Also, we looked at small and large mazes, and we considered configurations with a static maze and a static goal, static maze and a randomly placed goal, and completely random mazes. The observations for the agents consist in RGB information, as well as the depth channel provided by the Z-buffer, and the velocity of the agent in its egocentric reference frame. And the actions, although discrete, would provoke the agent to accelerate, either turn or move forward, backward, turn and move forward, or strafe sideways. So this problem is difficult because there are very few rewards in the maze, only one goal and a few fruits. And the agent needs to learn to explore. Moreover, we would like the agent, ideally, to derive some sort of spatial knowledge of a maze, to both know where it is and where the goal is located. So our contribution in this work is to show that reinforcement learning can be accelerated or even enabled in complex environments using auxiliary losses. And in particular, we focus on auxiliary tasks that have some relationship to the space in which the agent evolves, and which can help the agent derive some spatial knowledge of the environment. In particular, we look at depth prediction. So we can liken depth prediction to stereo vision from a single, predicting stereo images from a single molecular image, or local loop closure, which can be a way of exploiting the proprioception of the agent, so the knowledge of its velocity at every time step, and integrated over a short time interval to basically tell the agent that it's back on its footsteps, and use that signal to train the agent. Moreover, during the course of this project, we try to look at whether the agent is able to encode its own position and how it helps in the navigation. So, unsurprisingly, the architecture of the agent consists in a convolutional neural network encoder that takes in the RGB inputs, and then one LSTM or a stacked LSTM to have some hierarchical representation. In particular, since we use extra inputs, which are the reward of a past time step, as well as the past action and the current velocity, we can feed the past reward to the first LSTM, and this way we try to make it encode the goal location in a way, and then feed the velocity and action to the second LSTM with extra skip connections from the convnet. And of course, the agent is trained using reinforcement learning, in this case, asynchronous advantage actor critic. So the LSTM has extra policy and value function layers. And it also has additional outputs. The first kind of is depth prediction, which can happen both on the convolutional encoder, so it's depth from a single image, or depth from the integrated representation in the policy LSTM. Depth prediction, we considered different ways of doing it. Simply mean square regression of a depth image, but we noticed that it's actually more efficient to represent depth as a classification task, where we try to predict the depth quantization level at every pixel. And we actually work on a very coarse depth image with only 4 by 16 pixels. We also look at loop closure prediction as an auxiliary task on top of the a binary classification on top of the policy LSTM. So our architecture was compared to multiple baselines, to begin with the simple feed-forward agent, then an agent with an LSTM on top, then an agent with a convolution encoder and a stacked LSTM with additional inputs, and finally various ways of adding the auxiliary tasks to the navigation architecture. So in the static goal mazes, our agent actually can easily overpass top human performance, demonstrate as achieved by an expert game player at DeepMind. And so you can see how the agent navigates here in the maze. The baseline consisting of a feed-forward convnet is outperformed by the second baseline of convnet and LSTM on top, because it takes advantage of memory. The stacked LSTM may provide a little bit of advantage. So those figures are actually showing the cumulated reward over the course of an episode, averaged over 15 episodes, and averaged also over the top 5 performing agents. And we trained up to 100 million frames of Labyrinth. And it's when it start adding auxiliary tasks that the performance improvements really start to show. So this is with loop closure prediction. And the best performance definitely is achieved by adding depth prediction as auxiliary task, either on the convnet or on the LSTM, or combinations of other possible auxiliary tasks. And we can see that quite early on, during the training of the agent, we actually overtake human performance. So the question is, why would we use depth as an extra, as a task instead of an input? Well, there is a difference between being served information on a plate or actually trying to learn better presentations to make predictions. And we see that depth prediction as an auxiliary task definitely helps rewards. In random goal mazes, we managed to achieve human performance on smaller maze configurations. We are still a bit far from that on the larger mazes. And we also notice that so the agents with the auxiliary tasks of the blue and black curves and the green curve, so the ones on top, we notice that once the agent localizes the goal, it actually spends less time in returning to the goal, which means that it has derived some knowledge of its own position and of the position of the goal. And those results were observed in small mazes, not in larger mazes. We also looked at position decoding. So without actually training the agent to predict its own position, we only placed a decoder on top. And we can see that, well, as the agent starts navigating, initially it has no idea where it is, and then as it starts moving, it basically refines its position estimate a little bit like a SLAM algorithm. And I will just finish by showing this video, which illustrates the behavior of the agent in an eye maze. So you see the agent starts exploring one branch. Nope, nothing there. Found another branch, and then ultimately finds the goal, and in subsequent steps keeps coming back to the goal in the right branch. And I may perhaps move a little bit forward in the video and show you how it is doing depth prediction in a random goal maze. So you see that the depth prediction is quite coarse, but it basically fits to what the agent sees in RGB observations. And it does even a little bit of apple and goal detection. So thank you. Oops. Voilà. Thank you very much.
Thank you. Questions? Go ahead, Sergey.
So you mentioned that the results are averaged over the top 5 performing agents. So what does that mean? Like, how many agents are there total, and why did you use the top 5?
We considered a lot of hyperparameter configurations for training the agents. So, for instance, we will look at 64 seeds, and we would select the top 5 in terms of reward, the final reward.
Okay, I see. Thank you.
Hi, could you explain maybe a little bit about the intuition behind putting the rewards as well as action and velocity in the hidden states of the LSTM as well?
Yes, so if we feed reward as an input to the first layer LSTM, we can try to actually force the agent to, induce the agent to learn to remember what image is associated with a high reward. And this essentially would help encode the goal location. And we did some analysis visible on the poster of the representations of the agent, video presentations. And in terms of velocity, velocity provides an additional input which essentially facilitates a little bit the processing of sequential images. And this velocity is always in the agent self-referential frame. So it is velocity forward and sideways and turn.
Okay, thank you.
Hi, first thanks for the nice and interesting talk. So very recently there were actually 2 papers out of DeepMind regarding auxiliary tasks.
Yes.
And for me the main question is now, are you planning to compare these against each other? And also, is there any intuition so far in terms of which auxiliary tasks are very important for the problem?
Yes, so we think that depth prediction definitely is a very good auxiliary task, and we also think that pixel control and reward predictions are great tasks, yes.
Okay, thank you.
Hi, over here. Hopefully not too naive a question, but to what extent can you think about the auxiliary loss as kind of short-circuiting that sparse reward signal? And is there any intuition for why the results aren't as great as the mazes get bigger?
Well, we think that there is a capacity problem and also perhaps even a memory problem. The agent theoretically could perhaps encode all that information, but perhaps it's a matter of choosing better auxiliary tasks or changing also the architecture of the agent for larger mazes.
Right. Last one.
Have you tried applying these auxiliary tasks to robotics-like tasks with action spaces that are like joint positions and predicting things like first-order dynamics models?
Not me personally, but this is, I think, a very good suggestion.
All right, let's thank the speaker.
Thank you.
All right, this is the end of the morning session. There are posters up, the poster session, and we'll see you back after lunch.